So this part we take a look at how accurate is the meter or not. This little board here is just a capacitor discharge board for me to run the dynamometer through the paces and calibrate it to as accurate as I can practically do it. This trim port adjusts the output voltage. This will go from roughly about a little over 20 volt down to minus 0.2 volt, and I can switch the polarity. That means then it will go from minus 20 volt to plus 0.2 volt. I want it to cross the zero line, so that's why there's the minus 0.2 there. This one is the polarity button. I can switch that. This guy sees it right away. Of course, that guy, I have to switch all those buttons. This one switches the voltage. This is charge discharge control. Right now we'll be dealing with fixed voltage, and all of them are connected to all the channel at the same time. The plus go to here and here, and then I'm jumpering it across to connect to all the channels at the same time. So when I'm doing calibration or checking, I can check all 4 channels at once. So now I'm going to pause and zoom in. So now I got things positioned the way I want it to show the accuracy. You notice that I have a PC laptop here now. Because this will calculate percentage for me right away. This already discussed. The extra information column is the ADC reading, voltage, and the exact divider setting and multiplier setting. Here you can see the ADC 0, that's the reading, that's the voltage, ADC 1, reading voltage, ADC 2, reading voltage, and ADC 3, reading voltage, and the unity. The unity is 2.520 volt. And since I'm starting at divider at 6, so I'm at the maximum voltage range of about 30 volt. And I'm going to send this through the paces. You can see that at 2.5 volt. They're all reading roughly at the same range. And the biggest error I got here is the 0.5% error, not even 1%. We're going to drive this to as high as I'm comfortable driving it for now. So now at just a little bit over 20 volt, we can see the accuracy is pretty good. Right now the divider is engaged at 6 and the multiplier is in voltage following mode. That's pretty good. None of them exceed 1% error. None of them exceed 0.5% error actually. So I'm going to lower it. I don't want to leave it at 20 volt for too long because I think one of the capacitor may have leaked a little. At 15 volt, it's still doing pretty good. Look at the error rate, it's very respectable. None of them show more than 0.3% error. In a little lower still, this is a good place where I'll show one feature I have made. If I now switch to the divider to 0.3, you can see that the decimal point become an asterisk. There's an overflow. That way I can see exactly what the range max is instead of just the word overflow. I know that it isn't 15 volt. Divider 0.3 is the 15 volt range. It actually go up to only 14 and change. So now I'm going to lower it to below that, and you can see that the asterisk turned back into a decimal. Here we go. That's the maximum at the divide by 3 range, the 15 volt range. You can see that the error is very respectable at less than 0.2% error here for all 4 ADCs. I'm going to show you one thing. I'm going to change the voltage really quick, and you can see that the system would display a very much higher error rate, and I'm going to explain why something is showing that way. You can see a bit a little bitty, it flashes a 1% very quickly. Almost 2%. I think you saw that flash there. The reason is that this guy is reporting at 0.5 second, half a second. This guy is reporting at a quarter second. When the voltage is changed very quickly, in that quarter second difference, the voltage already changed significantly. We register a very high percent error. That's why to do proper calibration, I display the time difference between the two records. I am reading it about 200 milliseconds behind. The minus is ahead. This program is intelligent enough to, after it gets a record from the unity, it compared to the last record it read from the dynamometer. If the record is reasonably new, it will use it. If the record is too old, it will wait for the next one. The time it considered too old is self-adjusted so that the delta t is as close to 0 as possible. Another fact it recognizes, if the unity did a range change, most of you know that the unity will overshoot when there's a range change. This guy is intelligent enough to skip a cycle so it doesn't get impacted by the range overshoot here. So we see that at 12 volt it is very respectable. I'm going to lower it some more. 9 voltage, still very respectable, 0.1, 0.2% error. Closing in on 5 volt, 0.1, 0.2% error. Now you saw those jump there is because of the record time delta. Now we're on to the 5 volt range. This guy is still doing very good. While I'm still on the 15 volt range, I'm going to switch to the 5 volt range now. 5 volt range. The error is very good. 0.07% error. 0.09. Now it's closing in on the 2.5 volt range. Error rate is very respectable once it settles in. Again, 0.1, 0.0% error for all 4 channels. Now I'm going to go to the 2.5 volt range. S-string means overflow, as I said earlier. Pretty good error rate. Not as good as the other range actually is. I'm seeing some 0.2. The other guy was showing 0.0. Now we're going to go all the way down to close to the end of this range. At 1 volt, 1.6 volt, still pretty good. 0.0% error. 0.02. And I'm going to pick the next stopping point. Happen to be around 1 volt. And the error rate is very respectable. 0.0 something again. Further down still. At 0.4 volt. Around a 0.25% error. So far outside of when I'm changing things, you haven't seen a 1% error yet. Now we're into the real difficult area when the voltage is this low. Right now we're talking 140 millivolt. I'm going to switch to the most sensitive range and see how it measures. There's the 25th multiplied by 25. very respectable error rate, less than 0.3% error. Next stopping point should be around 60-70. That's where I expect some changes. Okay, at around 80 millivolts, error rate is very respectable at less than a quarter percent. Going back to a little bit higher, wait till it settles, it's less than a quarter percent. Oh, I'm going down. Why am I going up? Less than a quarter percent at 70. 34 millivolt. When it settles, you can see it's less than 1%. $13 millivolt, less than 1%, approaching 1%. We're seeing some 1%. Just a second, let it settle in first. Around 1% at 14 millivolt. It twitches to around 1%. Lower still. Below 10 millivolt accuracy is very difficult. Now we are definitely exceeding 1% error at pretty much 10.00 on the dot. This guy read 10.2. This guy is 10.25. It twitches a little bit because of the board. There's small oscillation there. Because of the discharge circuit doesn't hold as much as I like it to. 6 millivolt. Still reading very respectable number, 5.2, 5.25. 2 millivolt. Still reading very respectable number. And now we're down to about 5% error. This trim point must not be making good contact. Each time I touch it takes a while to settle in. At 0.5 millivolt, the error rate is huge, of course, but the number is actually meaningful. 0.4, 0.5, 0.4, and the actual is 0.6 millivolt. So the error rate is very respectable at a multiplier of 25 at the 200 millivolt range. Let's switch the polarity now. So I'm doing the minus 200 millivolt range. At minus 0.4 millivolt, this guy is measuring minus 0.7. Not bad at all. It's 50% error, but we are less than 1 millivolt. I want to get this over with, otherwise I'll switch the trim port. At 1.4 millivolt, this guy is giving me some very meaningful number. More than 20% error, but the number is still very meaningful once it's settled in. Millivolt. Now the error is starting to go down. It's below 5% error. At 20 millivolt, it starts to get very accurate. Now it's less than 2% error at 20 millivolt. minus 30 millivolt, you start to go below 1% error. Almost on the dot. 30.04, 30.1, 30.2, they're all below 1% error or twitching around 1% error. Then as you go up to about 60 millivolt, they're all below 1% error. Okay, when I randomly stop at a fixed voltage, the dynamometer measurement was pretty close to what the unity was measuring. All of them once went above 100 millivolt. They all look like they are at or below 1% error in comparison to the unity. So is it consistent through the entire range? To give you an idea what is going on here, right now I have the discharge board, the capacitor discharge board running, and we are at approximately 3.5 volt. So we're at approximately 3.5 volt. I'm going to leave this running in the background while I show you the accuracy across the entire range. This is a plot of the entire range as my program collects data while the capacitor is discharging. You can see the worst 25 reading. I don't know if you can read that because the letters are so small. So this is how the data is collected for calibration and validation. After I collected the entire spectrum, meaning all the ranges except the one using the divider is almost strict Ohm's law. There's some leakage of current into the op-amp, but by and large it is fairly linear, whereas the op-amp is not. So I collected all those when the divider is not engaged. So this black line here is the native ATMEGA328, no modification, no calibration, no adjustment. At 1 volt, the error is approximately 1%. At about 0.6 to 0.5 volt, the error is 2%. At 0.4 volt, 3%. 4% at about 3 volts. 0.29 volt right there. The last one there is 0.0494. That's close to 5% error. That's about 1/4 volt. At 1 volt, ATMEGA is 1%. My green line is way below the first minor marker, which would be about 0.2%. So this guy, the green line at 5 volt range, is below 0.2% up until about 300 millivolt. That's the 5 volt range, going all the way down. It's very consistent. The 2.5 volt again is very consistent, no overshoot here. The blue line. The very light cyan color one is my 200 millivolt range, and they are again below 0.1% for the almost entire range until it gets very close to 0. Light purple is my 5 volt range, and you can see that it is very consistently below 0.2% error rate. This one is my minus 200 millivolt range. Again, doing very decent, particularly when you take a look at this bunch in comparison to the ATMEGA unadjusted, uncalibrated. Let's zoom in a bit and take a look at close to the 1 volt range. 1 volt, 1 volt. Okay, now that we are at 1 volt maximum, you can see the 200 millivolt range, this light cyan color. I can probably do a better job calibrating. I don't know that it was the calibration. It could be when I was doing the validation run. There was some air conditioning, washing machine stuff going on. On the other hand, the minus 200 millivolt is doing very good. The minus 5 volt, very good, very good. The minus 200 millivolt, very good. And the plus 200 millivolt, very good, but certainly below 1% error. So the dynamometer, when the offset is properly adjusted, it does pretty good. Okay, now I'm selecting channel on. There's an option there for offset. When the offset is properly adjusted, it does pretty good. I will go into it in more detail when I'm talking about the circuit and the mistake. In summary, the dynamometer is doing a decent job, fairly precise, below 1% error. For the entire range down to approximately 100 millivolt-ish. That really is my goal when I set forth in doing it. The offset adjustment is a pain in the butt. I may fix that some point in time, but as it is good enough to use. In comparison to the ATMEGA native, which get to 2% error at about 0.5 volt, half a volt, whereas I go down all the way to 100 millivolt at 2% error, even for the high ranges, and far better for the lower ranges like the 200 millivolt range. So I'm fairly pleased with what I have done. The next part will go into the circuit, the lessons I've learned, and the error I made.